Hi everyone, here is the part 3 of our chapter 3. I hope you guys have seen the first two videos and we're going to continue with the orbital diagrams and electron configuration in this section as well. So remember we learned last time how you can write electron configuration. You follow that diagram that I showed you, starting the lowest energy orbital like 1s2, 2s2, 2p6, 3s2, 3p6 and so on. So we can also draw a partial orbital diagram which only shows us the highest energy sublevels being filled. Now here aluminum atomic number is 13. Okay, so if you want to write down the electron configuration, which is the full electron configuration, we're going to write it aluminum being 13. We're going to write the first orbital that is being filled is 1s. S can hold up to 2 electrons, 1 is 2. And then you have 2s, 2s2, and then you have the second level, you have 2p6. Maximum 6 can hold in p orbital. So right now we have filled 10 electrons and we need 3 more. So after 2p comes 3s. So 3s, s can hold 2, so you put 3s2. So after 3s comes 3p. So right now up to here we have filled 12 and we need 1 more. So 3p1. So that is the complete electron configuration for aluminum. Now the partial orbital diagram is you're only showing the highest energy sublevel being filled. So in this electron configuration there are 3 energy levels. So the first level is the 1s level, which is this is the 1s first level, and then you have the second level 2s and 2p, and then the third level 3s and 3p. So always the highest energy level is the highest s and p level, in this case which is 3s2 and 3p1. So you can draw an orbital diagram just showing the highest energy level, which is 3s has 2 electrons and 3p has 1 electron. Okay, we call that as the partial orbital diagram showing only the highest energy sublevels being filled. And another way that we can represent electron configuration is the condensed electron configuration. In the condensed electron configuration, we're going to write the symbol that represent the noble gas configuration that you find before the atomic number. So in this case, atomic number 13, aluminum. What is the noble gas that comes prior to aluminum? It is neon, right? Neon has 10 electrons. You can refer to your periodic table. Neon has 10 electrons and neon comes right before aluminum. So 10 electrons means 2 plus 2 plus 6, 10. So if you just write neon electron configuration, that would be this much. So in the condensed electron configuration, you can represent this as neon in square brackets, and then you write the highest electron configuration available, which is going to be neon, and then you write 3s2 3p1. Instead of writing the whole thing in the condensed electron configuration, you can write the noble gas prior to the element and then the last or the outermost electron configuration, which is 3s2 3p1. So that's how you write condensed electron configuration. Okay. Electron configuration and group. Elements in the same group of the periodic table have the same outer electron configuration. So in the same group, elements in the same group of the periodic table have the same outer electron configuration. So if you take group 1, what do we have in group 1? We have lithium, we have sodium, potassium, rubidium, cesium, francium. So those are the elements we find in the group 1. And all of those has S1 electron configuration. Elements in the same group have the same outer electron configuration. So that's going to be 1s1, 1s1 for the hydrogen in group 1. And then lithium would be 1s2, 2s1 because it's the period 2. So this would be 1s1, this would be 2s1. And then the potassium would be in period 3, that would be 3s1. So it has the same outer configuration. Lithium, sodium. Sodium would be 3s1, potassium would be 4s1, and so on. Okay, and then if you take group 2 has configuration 1s2, 2s2. So the outer electron configuration would be, after beryllium comes magnesium. So magnesium would be again 3s2 outer configuration, and then comes the calcium. Calcium would also be 4s2, and then you have strontium would be 5s2, and then you have barium, and then you have radon or radium. Okay, so likewise, but they have the same outer electron configuration, s2. And if you take the third group, so this would be 2s2, 2p1, 1s2, 2s2, 2p1. And then the next one, what comes after boron? So I forgot what comes after boron. Anyway, you guys can refer to that. Third, aluminum, I believe. Yes, right, aluminum. Yeah, aluminum would also be 3s2, 3p1, and it would have the same outer electron configuration. Same thing like for the carbon. After carbon comes silicon, nitrogen, and then you have phosphorus, oxygen, and sulfur, fluorine, chlorine, bromine, iodine, like that. So all of these, if you take one group, they have the same outer electron configuration, but depending on the period, so the energy level will change. Okay. Elements in the same group of the periodic table have the same outer electron configuration. Elements in the same group of the periodic table exhibit similar chemical behavior because it's always the outer electrons who participate in making bonds and doing some reactions. Since they all have the same electron configuration, they have similar behaviors. Okay, similar reactions. Similar outer electron configuration correlate with similar chemical behavior. Partial orbital diagrams and electron configurations for the elements in period 3. So what do we have in period 3? So in the period 3 we have neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. And we can see how the electrons have been filled up. So for the partial orbital diagram, this is in the period 3. So sodium is in group 1. The outermost shell has 3s electron and 3s1. And then the full electron configuration for atomic number 11 would be 1s2, 2s2, 2p6, 3s1. Remember, when you are filling the order up, you can follow the diagram that I have showed you in the previous lecture. Okay, so we can follow that. And condensed electron configuration would be neon is the noble gas prior to sodium. So right after neon, so neon has 10. So instead of all this, you can write neon and 3s1. And magnesium would be, after 3s1 comes 3s2. So neon 3s2. And for the aluminum, that would be 3s2. So after S comes P, 3s2, 3p1. Okay. And then P can go all the way up to 6. So P1, P2, P3, P4, P5, P6, like that. So this is how the electrons are being filled. Remember, first you will have to singly occupy them and then you start pairing them up. So we use the three rules that we normally use to fill up the orbitals. One is the Auer principle, meaning the lowest energy fills up first, and then you use exclusion principle. You can put two electrons in one orbital and having spins paired like this. And then the Hund's rule is when you fill up the same energy levels, first you have to singly occupy before you start pairing them up. See, 1, 2, 3, and then you start the next one, like that. And this is the partial orbital diagram and electron configuration for the elements in the period 4. Okay. Let me show you the diagram that I was referring to, what you can use to fill up the orbitals. So this is the diagram that I referred to you. This diagram right there. Okay. So this you can use to draw the electron configuration for any element. So we were here. Okay, so let me show you how we can fill up the electrons. Let's say you want to draw the electron configuration for, okay, so let's take element in period 4. Let's say you want to draw the electron configuration for nickel. You see, I'm going to choose nickel right there. Nickel atomic number 28. So we have to fill up nickel all the way up to 28. So I'm going to show you how to write this configuration that they have written over here. Okay, so nickel 28. So we're going to use this diagram. Remember that I showed you this 1s, and in the second one we have 2s and 2p, and then you have 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 7s, which is the diagram that I showed you the last video. Okay, now we have to fill up to 28. This is how we're going to do that. Always remember, S can hold up to 2 electrons, P can hold up to maximum 6, D can hold up to maximum 10, F can hold up to maximum 14. Okay, now let's see. This is how it's going to fill up. First, it's the S orbital that's going to form. So you draw that arrow 1s, and after 1s fills the 2s. After 2s fills up the 2p, then fills up the 3s. Once the 3s orbitals are filled up, you're going to go to 3p. Then comes the 4s. Then the 3d, 4p, and 5s. And then 4d, 5p, 6s, 4f, 5d, 6p, 7s, and 5f. That is the order of filling of the orbitals depending on the energy levels. So we're going to fill it up to 28. So first thing we're going to write is 1s. And s can hold up to how many? 2. So you can draw 1s 1s2. What comes after 1s? It's the 2s. You see the arrow is pointing to 2s. So 2s can hold up to 2. So 2s2. After 2s, it doesn't continue. So you go to 2p. So 2p. 2p. How many p can hold maximum? 6. So you put 2p 6. So after 2p6 comes 3s. So there would be 3s. S can hold up to 2. So you write 3s2. What comes after 3s2? It is the 3p. You see, after 3s comes 3p. 3p. P can hold up to 6. We have to go all the way to 28. So after 3p, what comes? 4s. So 4s, 2. And then after 4s, what comes after 4s? It goes to 3d. 3d. So D can hold up to 10. Now before we start filling up, we will see how many we have filled so far. So you can see here 1 is 2. There are 2 here. 2 plus 2, 4. 4 plus 6, 10. 10 plus 2, 12. Plus 6, 18. Plus 2, 20. So up to here we have filled up 20 electrons. And nickel is 28. So we need 8 electrons in the d orbital. So the complete electron configuration for the nickel would be, we're not going to put d maximum 10 because we only need 8 to make it 28. So the 3d will fill up to 8, 3d 8. That would be the electron configuration, the complete electron configuration for nickel. Now if you want to write down partial orbital configuration for nickel, what would be the noble gas configuration that comes before nickel? So you can refer to that. So nickel. So the prior to nickel comes argon. So here you can see the one that I was showing you, nickel 28. So it has full electron configuration. 1s2, 2s2, 2p6. Nickel, where are you? Okay, what's going on? All right, nickel. 28, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Okay, and this is the partial orbital configuration, which means showing the highest energy level, which is 4s2, 3d8, nickel, 4s2, 3d8. And then the condensed electron configuration would be, you write the argon, which is going to be your noble gas prior to nickel, argon, and then 4s2, 3d8. Okay, because argon goes up to 3p6. 1s2, 2s2, 2p6, 3s2, 3p6. That is 18. Argon is 18. So what's left is 4s2, 3d8. That's going to be the partial orbital configuration. And then the condensed would be argon and then the 4s2, 3d8. So that's what you are seeing here in the condensed electron configuration. And for potassium, that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. You use the same diagram that I have showed you in the previous slide, 4s1. So the condensed electron configuration would be argon and then the 4s1. Argon is the noble gas prior to potassium. And then calcium would be argon 4s2. 4s2, 3d1 would be scandium, because after the S you start filling up D. And then 4s2, 3d2, 4s2, 3d3, like that. Okay. And then when it comes to chromium, so when you come to chromium, you see these are your D electrons. there are 5d orbitals. So the chromium is 24. So let me show you what's happening in chromium. Let me open up another tab. Not a tab, but another slide. Okay, chromium. Let's see what's happening with the chromium. So chromium is 24. Chromium is 24. And we're going to use the same order to fill it up. So chromium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So this is going to be your valence shell. Valence means the outermost electrons that comes after the argon electron configuration. And up to here is your, up to 3p6 is the argon configuration, which is 18 electrons. Okay, so you have 4s2. So this is your s orbital. You have 2 electrons in the s level. And then you have d. And how many d orbitals are possible? 5. 1, 2, 3, 4, 5 d orbitals are possible. So this is your 3d level. And in the chromium 24, there are 4 electrons in the d level. So that 4 electrons are 1, 2, 3, 4. Okay. Normally these electrons, they become, or the orbitals become stable when they have half filled level or a completely filled level. Now the 3D can hold up to 5 electrons. Right now it has 4. So what's going to happen? So this is going to be 4s2, 3d4. To make it more stable, one electron from here, one of the s electrons, it could be any electron, one of the s electrons is going to jump into the empty 3d fifth orbital. So then the one of the 4 electrons of 4s2 going to go here. If it moves here, what would we have? We're going to end up having 4s1 instead of 4s2. Now you have 4s1. And then the 3d, instead of 3d4, it would become 1, 2, 3, 4, 5. It would become 1, 2, 3, 4, 5. It would be 3d5. So this happens when the d orbitals are about to be half filled like this, or when the d orbitals are about to be completely filled. Meaning if it is going to become 10 or 5, this thing happens. So the chromium electron configuration would be 4s1 3d5 instead of 4s2 3d4. Okay, so that's what you are seeing over here. Okay, you see here chromium 24, electron configuration is 4s1 3d5 instead of 4s2 3d4. So you can see here chromium. You see 4s1, 1, 2, 3, 4, 5. 4s1, 3d5. The same thing happened for the copper. Copper electron configuration, electron number or the atomic number is 29. So copper, if you write the electron configuration, it should be 4s1, 3d, 4s2, 3d9. It would be 4s2, 3d9. So let's go ahead and write electron configuration for copper. Let's do it together. So copper is 29. Okay, I'm gonna draw copper is 29. So we can start writing the electron configuration for 29. First, it's 1s2. Remember 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4p6, after 4s2 comes 3d10. Okay, 4s2 and then comes 3d10. Remember, I'm using this order which I have showed you earlier, this one right there. This is what you're going to be using when you're filling up. So after 4s2 comes 3d. Okay, after 4s2 comes 3d10. But let's see, we might not need all the way 3d10 because it's 29. So we're going to delete that. So right now we have up to 2 plus 2, 4 plus 6, 10, 12, 18, 20. So to make it 9, we only need 9 electrons for d orbital, copper 29. So the outermost configuration is going to be this part, 4s2, 3d, 9, because up to here, so this is going to be your noble gas configuration prior to copper, which is the argon, 18. So if you write the condensed electron configuration for this one, it would be argon, and then you have 4s2, 3d9. That's the condensed electron configuration. Okay. Now again, this is what we have. We have 4s2. And then for the d orbital, remember you can have 5 d orbitals. 1, 2, 3, 4, 5. And 9 electrons. They're going to be look like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now do you see here there are 9 electrons, and this d orbital would be so happy if it can become 10 and become stable instead of being 9. So they have extra stability when the d orbitals are either half filled or completely filled. Remember the chromium one? We made it 5 by having one from the 4s2. And similarly, the same thing is going to happen. So this is 4s2. This is 4s2, 3d, 9. So now what's going to happen? One of the s electrons. So one of the s electrons, it could be any of the s electrons, going to jump into this fifth d orbital, making it 3d10. So then the new electron configuration would look like this. In the 4s, now it has only one electron. And then your d orbitals would look like this. 1, 2, 3, 4, 5. It would have 10 electrons. So originally it had 9. There, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 1 electron came from S, making it 4s1, and this would make it 3d10. So copper would be, instead of 4s2 3d9, configuration is 4s1 3d10. So that's what you're going to have over here, copper. You see, this is the copper right there, 4s1 and 3d10. 4s1 3d10. So that happened for copper and chromium. So you see the chromium right there, 4s2 3d5, and 4s1 3d5 for copper, 4s1 3d5, and then for the, that's for the chromium, that's for the chromium, and then for the copper it would be 4s1 3d10. And that's the only difference, and the others will take the normal form. Okay. Okay. Periodic table of partial ground state electron configuration. So this is your periodic table, and then we can see, so the group 1, you can see group 1 excuse me, all of them has S1 electron configuration, outer electron configuration. Since it's the first period, 1s1, lithium would be 2s1, sodium 3s1, potassium 4s1, rubidium 5s1 excuse me, and cesium 6s1, like that. And then the group 2 would be 2s2, 3s2, 4s2, 5s2, 6s2, like that. So for each group we'll have the same outer electron configuration, but then the period number will change. Okay, same thing. So we call this, so these are the first two blocks, first group, you see, it's the S electrons are being filled. So we call it as main group element. This is S block element. This is S1 being filled up, and this is S2. So this is called S block element. And then the transition elements, which is, we call it as D block element, because now we start filling up D electrons. 4s2 3d1, d1, d2, d3, d4, d5, d6, d7, d8, d9, d10. So since the d electrons are being filled up in the blue section, we call it as a D block elements. And then over here, going from group 3 to group 8, p electrons are being filled up. S2P1, S2P2, S2P3, S2P4, like that. P1, P2, P3, P4, P5, P6. So we call this block as P block elements. Okay. And then in the periodic table, you see in the D block, under the D block, so here's 57 and then the 72. So from the 58 to 71, this section, F electrons are being filled up. So we call it as inner transition elements or F block elements. And then from 89 to 104, there is a gap, which is 90 to 103. That is also F block elements. That is the period 6, and this is period 7. So this is 4f orbitals have been filled up, and these are 5f orbitals are being filled up over here. This is the 4f and this is the 5f. So the periodic table, we can categorize them based on which orbital is being filled up. So we have S block elements, first two groups, and then we have D block elements from this transition element section, D block, and then you have P block elements, this section, and this is F block elements right here. Okay. Are we done? Orbital filling and the periodic table. So this diagram shows us which electrons are going to fill in each section. So this is the first section, S orbital, 1s, and then the 2s, 3s, 4s, 4p, 1s, 2s, 3s, 4s, 5s, 6s, 7s. And then from the 1s, it goes to nothing, because it's still the S orbital, S2, 1s2. Hydrogen is 1s1 and helium is 1s2. And then you have the 2s, 2s2, and then the 2s goes to 2p. So 2s goes to 2p. So this right here. And then after 2p comes 3s. And 3s also directly goes to 3p. After 3p comes 4s. 4s. And then once the 4s is being filled up, it goes to 3d. 3d. And then goes to the 4p. And then you have 5s, then goes to the 4d, and then you have 5p. Then you have 6s, and then that gap we have 4f, and then the 5d. This is the 4f, and then the 5d, and then 6p. This is the 7s section, and then comes the 5f, 6d, 7p. So here's another way to look at how the electrons are being filled up. But if you follow the diagram, that the zigzag pattern that I have been using to show you how to fill up the electrons, that should be good enough. So if you follow that and know how to fill up the electrons, then for any element in the periodic table, you can come up with the electron configuration. I'm going to stop this section here, otherwise it's going to get a little too long. So I'll come and talk about categories of electrons in the next section.